All right, so today we're going to learn about the normal distribution. A normal distribution has a couple different names. Sometimes we describe it, or it's called a normal distribution. Other times it's called a Gaussian distribution, named after the mathematician who discovered it, Carl Gauss. Other times we just call it a bell curve because the shape of it looks like a bell. And it's shaped like a bell. A lot of things in life model a bell curve or a normal distribution where most people are pretty average at whatever we're talking about. The farther you go out, there's fewer and fewer people. That would be by the height here. If I go out really far, there's very few people out here. There's very few people out here. So if I was thinking about something like height follows the normal curve, most people are pretty average height. And then I have some people who are taller, some people who are shorter. But if I think about people who are really tall, like in the NBA, there's very few people out here. And if I think about people who are really short, there's very few people out there as well. Most people are right here. It's used for like IQ and other things like that too. When we want to talk about our position in the distribution, a z-score is going to help us out. So the formula for z-score is this right here. It's z equals x minus mu over sigma. And this x is going to talk about our position. So if you wanted to find out your z-score for the SAT or your IQ or your height or whatever it is, this is your position minus the average over the standard deviation. And this notation here says that n means we're looking at a normal curve. The first number is our mean, and the second number is our standard deviation. The z-score is going to tell us how many standard deviations above or below the mean we are. Okay, so we'll look at an example. We're going to start out pretty easy. It says, suppose that we have a normal distribution with mean 5 and standard deviation 6. This says that x is a normally distributed variable with mean 5 and standard deviation 6. Suppose x is 17. We want to find our z-score. So we're going to do the score of 17 minus 5 over sigma. And since we're above the mean, we know this is going to be positive. Oh, I shouldn't have said sigma. I should have said sigma is 6 in this problem. So 17 minus 5 is going to be 12 over 6, 2. So what that means is this score of 12 or 17 is 2 standard deviations above the mean. And we're going to be saying in words what we're talking about here. My writing is not going to be the best on this tablet that I'm using. So this says 2 sigma above mu. Okay, I would recommend that you pause the video at this time and try to do this problem. Okay, the answer to that was z equals 1 minus 12 over 3. That would be negative 11 over 3, which is a decimal. So we'll do negative 11 over 3 is negative 3.6 repeated. This means the score of 11 is way below the mean. Okay, we're going to do some interpreting now. So it says, some doctors believe that a person can lose 5 pounds on average in a month by reducing his or her fat intake and by exercising consistently. Suppose that weight loss is a normal distribution with x as the amount of weight lost in pounds by a person in a month. Use the standard deviation of 2 pounds, so that says the mean is 5 and the standard deviation is 2, to fill in the blanks. So it says, suppose a person lost 10 pounds in a month. The z-score of x equals 10 is 2.5. Verify. So I'll do that real quick. 10 minus 5 over 2 is 5 divided by 2, or 2.5. Okay, so the z-score is 2.5. Standard deviations to the, it's positive, so we're going to say right of the mean. What is the mean? The mean is 5. Okay? Next, we're going to say, suppose that a person gained 3 pounds, which is a negative weight loss. Then z equals what? So we have to go over here. The value is negative 3 minus 5 over 2. This is negative 8 over 2, which is negative 4. The z-score of negative 4 tells us that x equals negative 3 is negative 4 standard deviations to the left of the mean. Because it's negative, we know it's to the left. Oh, and just so we know here, the z-score is a standardized score. So I'll write that off to the side here. Z is a, sorry about that. Z is a standardized, oh, I don't know what happened there. Z is a standardized score. So it always tells me how many standard deviations, and it helps me compare things that are hard to compare. So like, if I wanted to compare SAT and ACT scores, for example, I should be able to compare those things. Colleges compare those things to say if you got into a school or not. So they use a standardized score to say how many standard deviations above or below the mean were you. Let's look at part C. Suppose that random variables x and y have the following normal distributions. X follows this normal distribution and y follows this normal distribution. If x is 17, then z is 2. This was previously shown. And then if y is 4, what is z? So now we're looking at, this is kind of like ACT and SAT scores. Not exactly, because those aren't the mean and standard deviations, but I want to compare two different things that have different means and different standard deviations. So for y is 4, I'm going to use the y mean, 4 minus 2, over 1, and I got 2 again. So what this means is that a score of 17 on the x distribution is the same as the score of a 4 on the y distribution, because we're just as above the mean according to the standard deviations here. Okay, pause the video and try this one here. Okay, so it says Jerome averages 16 points per game with a standard deviation of 4 points. Suppose that Jerome scores 10 points in a game. The z-score is negative 1.5. So this means that 10 is negative, or sorry, not negative. I should say that it is 1.5 standard deviations to the left, because it's negative, of the mean, which is 16. Okay? Oh, and this is twice, so we don't have to do that one. We already did it. Okay, now we're going to talk about the empirical rule. Sorry about this, I started over, so I missed some of my stray markings. The empirical rule is the 68, 95, 99.7 rule. And this is just a rule that will help us understand what a normal distribution tells us. So if I look at this normal distribution, our mean is here. If I go out one standard deviation, if I go plus or minus one standard deviation, this will tell me that that is 68% of the total population. Okay, so that's a little bit harder to understand when we're talking about just abstract numbers like this. So let's talk about IQ. Again, I'm going to look at IQ, and the average IQ score is 100. So if I go out to, for IQ, it's a normal distribution with a mean of 100 and a standard deviation of 15. So if I add 15 and subtract 15 here, that means that 68% of the population has IQs in this range here. Okay? Most people are going to be between 85 and 115. If I go out a little bit further, let's say I go out to 2 standard deviations, and these increments should be the same. It's just, I'm just sketching things here and they don't look exactly the same, but this distance here should be the same as this distance and this distance and this distance. If I go out 2 standard deviations, that's going to be another 15, that's 130, and I'll subtract another 15, that'll give me 70. 95% of people would fit in this distribution here, or 95% of people fall within 2 standard deviations. So 95% of people, okay, and that's talking about this area here, would be 0.95. 95% of people fall between 70 and 130 IQs. Once you start to get out past that, that's when you get labels like genius and things like that, because you're out you're out past 2 standard deviations or past 3 standard deviations. So if you probably figured this out by now, if I go within 3 standard deviations, that's 99.7% of people. Okay, and that would be 145 and 55. Okay, 99.7% of people fall in this range here. And this is 99.7. There are still people out past that. That's going to be your ultra geniuses or the people who, really have trouble understanding things. So that's why it's only 99.7. There are people out here. There are people 3 and 4, and you could go, very high out here. It's just the farther out you go, there are very, very few people out there. Or it doesn't always have to be people. We could be talking about the average battery length of your phone or whatever it is. It's normally distributed. The farther out you go, the fewer and fewer people there are, or fewer and fewer batteries. Okay, so now we're going to look at this. I don't know why the book chose to show things in this order. We're going to use the empirical rule on example 6.5, but we're going to go over this problem first. It says, from 1984 to 15 to 18-year-old males in Chile had a mean of 172.36 and a standard deviation of 6.34. So out to the side here, I'm going to say y is a normal distribution with mean of 172.36 and a standard deviation of 6.34. And just above this, I'm going to say that y was 1984 to 1985. Just so it's a little bit easier to keep track of things. And then for x, it says here that in 2009 to 2010, so this is in the future, we are going to have an average height of 170. So that's normal distribution. The mean is 170, and the standard deviation is 6.28. So at a glance, we can see that people were taller in 1984 to 1985 in Chile. They're shorter now. They were more spread out. They're more spread out now, though. And there could be tons of different factors that could cause that. But what we want to do is we want to compare someone who is 160 centimeters tall now, or in 2009, compared to y, which was 162 centimeters then. So I said before that a good way to compare things when we have different means and different standard deviations is with a z-score. So what we're going to try to figure out is who was taller for their time. Like obviously the y value is taller, but everybody was taller back then, so we're trying to figure out who was taller for that time. So we're just going to do the z-score. Z is 162.85 minus the mean, which was 172.36, over 6.34. And before I pull up my calculator here, I'm going to set up this one too. This z is going to be 160.58, because that's the value I'm interested in, minus the mean, over the standard deviation, 6.28. So let's pull that up on the calculator here. For our y distribution, we're going to do 162.85 minus 172.36. And then I'm going to divide that by the standard deviation. Notice I'm doing the order of operations, so I hit enter first. So this z-score here was z equals negative 1.5, meaning that they were about 1.5 standard deviations below average. And now let's look at the next one here. We have 160.58 minus 170. And then I'm going to divide that by the standard deviation of 6.28. And we also got negative 1.5. Okay, so what that means is both of these people were just as below average as each other for the times, because they were both 1.5 standard deviations below average. Okay, so now let's use the empirical rule to explain what this distribution means. Again, I think that it should have been in a different order here, but let's explain this distribution. We're going to say, I'm going to draw a quick sketch of it. Again, sorry it's not quite straight there, but you know, I'm using this weird tablet. So the mean is 50, and the standard deviation is 6. So this would be 56 is one standard deviation below or above, and below would be 44. So what that means is 68% of the data is between 44 and 56. I just use the plus sign for there, for and, because it's hard to write with this thing. So now let's go out 2 standard deviations. So I'm going to add another 6, that would give me 62. And subtract another 6, that would give me 58. So 95% of the data is between 50, oh, I did that wrong. That should have been 38. Is between 38 and 62. And again, that's because we're using the empirical rule. It says if I go out plus or minus 1 standard deviation, it's 68%. If I go out 2 standard deviations, it's 95%. And if I go out 3 standard deviations, it's 99.7%. So let's do the 99.7. If I add another 6, because my standard deviation is 6, that's 68. And if I subtract another 6, that would be 32. This was 38. So we're going to say 99.7% of the data is between 32 and 68. Okay, at this time you should pause this and try to do the try it problem. Okay, for the try it problem, it just said we had a normal distribution with mean 25 and standard deviation 5. 68% is 1 standard deviation. So we say 68% is between, that would be 20 and 30, because we just added 5 and subtracted 5. Okay, So now we're going to go on to the next section here, 6.2. And in this section, we're going to use the calculator to actually figure out what the standard or what the normal distribution is telling us. So before we get started, this is a probability distribution. And if you remember from before, the total area under a normal any probability distribution is 1, because the total area has to add up to 100%. What this is telling us right here is that if I take the area to the left and the area to the right, if I add those two up, it will always equal 1, because it has to add up to 100%. So you can either be below this value or above this value. The probability that something is exactly one value is always 0, because it's a line, and lines don't have any area. It's kind of like saying, like, I'm going to guess your height. I'm going to guess that you're 156.274 centimeters tall. Nobody is going to guess exactly right anytime, because measurements can be so imprecise. So anytime if you try just one particular value, the probability would be 0. So we're always going to look at ranges of numbers, like this shaded area here. We're going to start with an easier problem. It says the area to the left of the curve is 0.228. The area to the right of the curve, we just do 100% minus 0.0228, and we get this value of 0.9772. To approximately summarize that, we say if the area to the left is about 2%, the area to the right is about 98%. Okay, can you try this one here? So all we should have done is 1 minus 0.012, 1 minus 0.012, we get 0.988. That means if the area to the left is about 1.2%, the area to the right is 98.8%. Okay. So now we're going to actually take this into real life. We're going to be using our calculator a decent bit. The calculator does most of the work for us, though, so it should be pretty easy. So it says here, the final exams in a statistics class were normally distributed with a mean of 63 and a standard deviation of 5. I'm going to write that off to the side here. Normal distribution, mean is 63, standard deviation is 5. It says find the probability that a randomly selected student scored more than 65 on the exam. So I'm going to sketch this curve to get an idea of what I'm talking about. The mean is here, 63. I want to know what's the probability they got above a 65. That's 65. So I'm going to type this in the calculator. The calculator will tell me the area to the right of the curve. So we're just going to do this. Second, distributions, normal CDF. My lower bound is 65 because I want the area to the right of the 65. My upper bound is any score higher. So the way that we're going to do this is we're going to write 999 because nobody is going to score a 999 on a statistics exam. It's way too high. For the most part, we're just going to write 999 if it doesn't hit the top, and if it's on the bottom, if it's shaded off to the bottom, we're going to do negative 999. Okay, so the mean is 63, and the standard deviation is 5, which I have written right up here. We'll hit enter a couple times, and we get that the answer was 0.34457. And to show your work for this kind of problem, you just tell me what you type in the calculator. We did a lower bound of 65, an upper bound of 999, a mean of 63, and a standard deviation of 5. And if we look here, oops. Oh, come on. Okay, if we look here, I just wrote down what it says here on the calculator, and we got that answer of 0.344, which means about 34% of people scored above a 65. Not the best. Okay, so find the probability that a randomly selected student scored less than an 85. Well, if that many people scored below a 65 or above a 65, the probability of below an 85 is going to be very high. They scored pretty low on this test. So we're going to draw that curve again, find the probability. They scored below an 85. So 85 is here. We're finding below. So we're going to do normal CDF again. And PDF we're not going to use at all. It's just not going to be helpful in this class. We're going to always use normal CDF. So the lower bound this time is negative 999 because I trail off forever in this direction. And my upper bound is 85. The calculator remembered those two other answers. So we'll just hit enter a couple times here. The probability of that is positive 0.999. So it's basically certain that a randomly selected person scored below an 85. Just about everybody scored below an 85. And again, to show our work, we just write this step down again. But, for the sake of this, you saw what I did on the calculator. But if I asked you on a test to show your work, you would just write down this right here. Normal CDF, negative 999, comma 85, comma 63, comma 5. Okay, now this problem's a little bit different. It's asking for the 90th percentile. That means that we're interested in the probability, the value here, where the area below it is 90%. Okay, so on this one, we know the area. The last one, I wanted to find the area. I knew the values. This one, I know the area, and I want to know what is this value. So on the normal CDF problems, it doesn't matter. We can pick a lower bound. We can pick an upper bound. On the inverse problems, we're going to use inverse normal on these problems. It will only tell us percentile. So it will only tell us the high value. Okay? There's ways we could do this if I wanted to figure out this value over here. But let me just go ahead and do the problem. So we're interested in what value has 90% of the data below it. So all we're going to do is say second distributions. Last time I knew my values, so I used normal CDF. This time I know my area and I'm looking for a value, so I'm going to use inverse normal. And if you type the wrong thing in, it'll ask you for area. If you're doing problem B, you don't know the area, so you would know, oh, I did something wrong, I better go fix this. So anyway, the area is 0.9. The mean in this problem is still 63. And the standard deviation is 5. So this tells me that a score of 69.4 would be the 90th percentile. 69.4 is the 90th percentile. And if you wanted to show your work on that one, you just write inverse norm. The area was 0.9. The mean was 63. The standard deviation was 5. Again, I'm just writing down this to show my work. The calculator is doing all the work for us. You just tell me, what did you type in the calculator? That way, if you make a mistake, I can see where your mistake was. Okay, finally, find the 70th percentile. And it says that 70% are below and 30% were above. If I want to say, like, what score told me where the top 30 was, I would do inverse norm for 70% because the calculator only tells me below a certain value. So again, we're going to sketch this. 0.7, 0.3 is over here. I'm interested in this value right here. We do inverse normal. The area that I'm interested in, the area to the left, it's always to the left, is 0.7. We're still looking at a 63 and a standard deviation of 5. I'm just going to hit up, up, enter. And I'm going to replace that 90 percentile with the 70 percentile. 70th percentile would be a score of 65. 65.6. Okay? All right. Oh, geez. All right, so at this point you should pause and try this try it problem. Okay, it says the golf scores for a team were normally distributed with a mean of 68 and a standard deviation of 3. Find the probability that a randomly selected golfer scored less than a 65. So I'm going to draw my distribution. My mean is 68. I want to know less than a 65. That's a value on here. I'm going to shade to the left because it's less than. So since I know the values, I'm going to use normal CDF. If I knew the area, I would do, or the probability, I would do the inverse norm. So we're going to do second distributions, normal CDF, lower bound. I can leave that as -1 times 10 to the 99th power. You know, we did -999. The calculator said, oh, I'll do one better. That's -1 with 99 zeros after it. So that's a really, really big number. It's going to give me the exact same answer if I just did -999. So the upper bound is 65, the mean is 68, and the standard deviation was 3. Okay, so we got -999, 65, 68, and 3. And the probability of that is 15.86%. Okay, so now we're going to look at the probability. We're going to look at a probability distribution. So now we're going to look at a normal distribution for personal computers. It says people use their computers for all kinds of different things: home, research, communication, personal finances, blah, blah, blah. Suppose that the average number of hours a household uses for a personal computer for an entertainment is 2 hours per day. Assume that the times for entertainment are normally distributed with a standard deviation of 1.5 hour, or is a half of an hour. So we have a mean of 2 and a standard deviation of 0.5. So it says find the probability that a household computer is used for entertainment between 1.8 and 2.75 hours. Well, we're just going to draw our normal distribution. The mean is 2. We're looking at between 1.8 and 2.75. These aren't perfect approximations, but I'm interested in this area here. We're just using that normal CDF again. Second distribution, normal CDF. The lower bound in this case is 1.8, because that's the lower bound right there. And the upper bound is 2.75. The mean in this problem is 2, and the standard deviation is 0.5. The probability of that is about 58%, 59%. So the answer to this one is 0.588 6. And to show your work, you would just write what you typed in the calculator. So now it says find the maximum number of hours per day of the bottom quartile of the households. So they're trying to trick us on this problem by using the word quartile instead of the 25th percentile. The bottom quartile means that this is the bottom 25%. If they asked us for the upper quartile, that would be 75%. Because remember, quartile 1 is 25%, the median is 50%, quartile 3 is 75%, and there is no maximum or min on these problems. So anyway, we're just going to do inverse normal. Because I'm looking I know the percentage. I know the area. The area is 0.25. The mean is 2. And the standard deviation is 0.5. So the bottom quartile is 1.6 hours for entertainment. Okay, at this point you should pause the video and try to do this try it problem. Okay, in this problem, they gave us the mean and standard deviation from before, and we just want the values between 66 and 90. This is my lower, this is my upper. So we just type that in the calculator. Second distributions, normal CDF. This is getting repetitive, but it's important you remember how to do this because this is going to be important on the test. The mean was 68 and the standard deviation was 3. Probability of this is 0.495. So this means is about a 50% chance that someone on the golf team scores between a 66 and a 70. Okay, so now we're going to look at the average age of smartphone users. We're saying that they are normally distributed between ages 13 to 55 plus, and we're going to look at the ages of those people. If you think about that, that's probably true. Most people using smartphones are probably well between 13 and 55. If you go out really young, there's very few people who are 13 who have smartphones, and if we look at older people, they're more likely to say, just give me my flip phone. I don't care about the new smartphone. So most of the people are going to be in between these two. So we said the average age is 36.9 and the standard deviation is 13.9 years. I'm just going to write that off to the side so I can see it more clearly. 36.9 and the standard deviation of 13.9. Determine the probability that a random smartphone user between the ages of 13 and 55 is between 23 and 65.7 years old. This is our lower. This is our upper. We're going to type that in the calculator. Let's clear this out. So I'm going to do distribution. 23 is my lower bound. 64.7 is my upper bound. The mean is 36.9. And the standard deviation is 13.9. Which means that our probability of that is, that's a pretty wide range of numbers, between 23 and 64. So it's not surprising that was a probability of 81%. 0.8185. So that was a fairly high probability. Okay, now we're going to find the probability that a randomly selected smartphone user is at most 50.8 years old. I just forgot to draw my normal curve. It is going to be important that you draw the normal curves. It's just going to help us get an idea of what we're trying to find and see if our answer makes sense. So we want an age of 50.8 years old. At most means I'm shading up to 50.8. So we're going to do normal CDF again. Since my lower bound goes the whole way down, I'm just going to pick negative 999. The upper bound is 50.8. The mean is still 36.9 and the standard deviation is still 13.9. So the probability of this is 0.8413. So again, a very high probability that the average smartphone, a random smartphone user will be below 50.8 years old. That's again Not surprising, a lot of people using smartphones are younger. Okay, now we want to find the 80th percentile. This is giving us a percentage on this problem, so we know we're going to use inverse normal. This is an area of 0.8. So we're going to use inverse normal because we know the area and I'm looking for this value. Second distribution, inverse normal. The area is 0.8. The mean is 36.9. And the standard deviation is 13.9. This tells me that the 80th percentile is 48 and a half years old. We'll call that 48.6 years old. Okay, at this time, you should try this problem where you're looking for the 30th percentile. It wants you to interpret it in a complete sentence, and then find the probability of a random smartphone user is less than 27 years old. Okay, for part A, it's a percentile. So that means that the area is 0.3. The area to the left is 0.3. So I'm going to copy and paste this because it's the same numbers as before. But I'm going to change the 0.8. But I'm going to change the 0.8 to 0.3. So that percentile is 29.6. So it says interpret this in a complete sentence. That means that 30% of smartphone users are below the age of 29.6. Because remember, a percentile tells us the percent that's below a value. For part B, find the probability that the age of a randomly selected smartphone user is less than 27. We're going to do less than 27. We're shading to the left because it says less than. I'm going to copy this normal CDF problem here because this has the same mean and the same standard deviation. The lower value is negative 999, which is cool. That's what I already got here. The upper bound is 27. So the probability that a smartphone user would be below 27 is 23%, 20.2381. Okay, and then looks like we only have a couple more problems left to do. It says in the United States, the age is 13 to 55 smartphone users. Follow normal distribution, same as before. This one, it wants us to calculate the interquartile range. So this is a way they're trying to trick us again by asking us to do the exact same thing we've been doing, but we need the quartiles. So I need to know this 25% value for quartile 1, and I need to know this 75% value for quartile 3, and that's saying that this is 0.75. So I'm going to do two problems here. We're going to do inverse normal for 0.25. So Q1 is going to be, it's the same values as before, so I'm just going to copy and paste this guy. It's still a mean of 36.9 and still a standard deviation of 13.9. But instead of 30th percentile, I'm looking for the 25th percentile. So the quartile 1 was 27.5. You know, because 27-year-olds always say, I'm 27 and a half years old. For quartile 3, I'm just going to copy and paste this guy again and change it to the 75th percentile. So the quartile 3 is 46.2. So we're just going to do the IQR is 46.2 minus 27.5. And I can do that kind of quickly here. I can just copy and paste this value minus the quartile 1 and we get the IQR is 18.75. Part B says 40% of the ages range from 13 to 55 plus are at least what age? So 40% are at least. This time we're saying 40% are at least. So I'm looking actually at this side here. 40% are at least this age. So since we're looking at 40% are at least this age here, that means that the value to the left is 0.6. So I'm going to do inverse normal. And instead of doing the 40 that I would have predicted, I'm going to do this 60% because of the way it was worded. So the area is 0.6. These are the same values as before. So I'm going to copy this and change the 75 to 0.6. So this value is 40.4. Okay, so at least 60% of people are under the age 40.4, or another way of saying it is 40% of people are at least 40.4. At this point, you should pause it and try this problem. Okay, it says calculate the first and third quartile. So you're going to do inverse normal for 0.25 and 0.75. I don't know why it's jumping around like that. And so we're going to do, I'll clear this out. Second distribution, inverse normal. The area in this problem is, I'm looking at 25%. Ooh. Oh, it always has to be a decimal too, because the area has to be below 1. If you accidentally hit like 25 instead of 0.25, it'll give you the wrong answer. And we go 81 and 15. So the 25th percentile is, sorry, the first quartile is 70.8. In the quartile 3, I can just copy and paste this. And change that to a 75. So that quartile 3 is 91.11. Okay, next it says find the middle 50%. Well, the middle 50% are between what two values? The middle 50% are between quartile 1 and quartile 3. So we could just say this answer right here. Part B is the middle 50% are between 70.8 and 91.11, and that's because that's what the quartiles actually tell us. Okay, we got one last problem here. This is a citrus farmer who grows mandarin oranges, finds that the diameters of the mandarin oranges harvested on his farm follow a normal distribution with a mean of 5.85 and a standard deviation of 0.24. Find the probability that a randomly selected mandarin orange from his farm has a diameter greater than 6. Sketch the graph. So we're just going to draw 6, shade to the right because it says greater than. You're seeing that as we get the hang of this, as I've done a ton of these, I'm getting a little bit less specific with my graphs. That's because I really just want to see what value am I looking at and am I shading it above or below. So we're going to look at normal CDF. The lower bound is 6. The upper bound is 999. No orange is going to be that big. We're going to look at mean of 5.85 and the standard deviation of 0.24. That is a probability of 0.2659. Find the middle 20% of the oranges. So the middle 20%, we're going to be looking at the middle here. That's going to be plus 10%, minus 10%. So we're going to look at 50. This is going to be a total area of 40 and 60, because that would leave me the middle 20% there. Okay, because there's 20% left over in the middle. So I'm going to find this number minus this number. I'll call this x1 and x2. So we're going to do inverse normal again. The upper bound there is inverse normal for an area of 60%, or 0.6. The mean is 5.85, and the standard deviation is 0.24. So the x1, our upper limit, is 5.9, and that's the centimeters for the orange. And then I'm going to copy and paste this again to find that 40 percentile. And that's 5.7. So the middle two are between 5.9 and 5.7. I should probably change the order of those, because you normally want to say the smaller number first. And finally it says find the 90th percentile and interpret that in a complete sentence. So we're going to do inverse normal. And for the 90th percentile, just change this to a 9. That means that 90% of oranges are less than 6.15 centimeters in diameter. Okay, at this point there's one last problem for you to try. If you wouldn't mind pausing it and trying it. Okay, so the middle 40 percentile are between these two numbers. The middle is here. I'm going to go 50 minus 20, this is going to be 0.3, and 50 plus 20, that would be 0.7. So I'm going to copy this again. 0.7, 5.97, and for the other one, we said that was 0.3, that's 30%, 5.72. Okay, and then finally it says find the 16th percentile and interpret that in a complete sentence. We're going to copy this again and write 16. This 16th percentile is 5.611, and in a complete sentence I would just say that 16% of oranges are smaller than a diameter of 5.611. So that's it for this video, for this lesson on the normal distribution. We talked about bell curves. We talked about the empirical rule that said that 68% of the data is within 1 standard deviation, 95 is within 2, and 99.7 is within 3. We talked about using normal CDF, and that's when I'm looking for limits when I'm given a value here. If I have an area and I say what value or what percent of the data is between this number and that number, and we use inverse normal, and that's used to find percentiles. That's when they give me an area or whatever. They give you an area here and you're looking for this value at the bottom. So I hope that was helpful for everyone. I hope everyone has safe travels if you're traveling, and I hope you enjoy your class watching the lecture from home. All right, so that's it for today.